Today we're going to be proving the Cauchy-Schwarz inequality. Simple proof. Let's say we have two non-zero vectors, x and y. They belong to the set R of n, non-zero. The Cauchy-Schwarz inequality states that the absolute value of the inner product of x and y is less than or equal to the product of norms of x and y. The only time where it equals each other is less than or equal. The only time when it equals is when x equals y times by some arbitrary scale. Let's call it lambda. So let's say we have a function f of lambda y, f of lambda. It's going to equal the norm of lambda y minus x squared. Now, if you recall, the norm of a vector, let's just say z, is just equal to the square root of its components squared and added to each other. So there's the x component, the y component, dot dot dot, the nth component. You can see that. So we can say that it's greater than or equal to 0. So for this one, we can say it's greater than or equal to 0. Furthermore, the norm squared is just the vector dotted with itself, the inner product itself. So we can just say that it's the inner product of lambda y minus x, lambda y minus x, which is greater than or equal to 0. Now we can use the associative, the distributive, and the commutational attributes of the set to just treat this not exactly, but sort of like regular multiplication, but this is a vector multiplication. So we have lambda y times by lambda y is just lambda squared, so we just take that out. Then we get lambda y times by minus x. It's going to be minus x. The same thing here. And then minus x times by minus x, positive. So positive x with itself, or being greater than or equal to 0. So we can just make this a bit nicer to read right in one line. Lambda squared minus 2, because we have 2 of these, x of y, taking out the lambda, plus x dot with itself, greater than or equal to 0. Now, we can just rewrite this as, make this nicer to read. We can call y with y alpha. We can call 2x and y beta, and we can just call this term gamma. So we're going to get gamma lambda squared minus beta lambda plus gamma is greater than or equal to 0. Now it just looks like a typical quadratic, right, in its most basic form. So to find the minimum of a quadratic, we usually substitute in minus b over 2a, or in our case, minus beta over 2 alpha. But because we have a minus here, we're just going to substitute in beta over 2a. So when we do that, we get alpha times by beta squared over 4 alpha squared minus beta squared over 2 alpha plus gamma is greater than or equal to 0. take this here. We simplify this, we're gonna get alpha minus beta squared over 4 alpha less than or equal to 0, greater than or equal to 0. So let's get all the alphas and gammas on one side and the betas on one side. So we're gonna get 4 alpha gamma is greater than or equal to beta squared. Right, so now we're at this form. We can just substitute in these values. We're going to get 4 times by alpha, which is y, inner product of y with itself. Remember the inner product of a vector with itself is just the norm squared. So it's going to be y squared times by gamma, which is same case, greater than or equal to beta squared. So it's going to be 4 x and y squared. Right. So we can simplify this down. And when we simplify it down, we divide by 4 and we square root. We're left with total value, the absolute value of the inner product of x and y is less than or equal to the norm, the product of the norm of x and y. And that is the Cauchy-Schwarz inequality.